In today's session, we will discuss some of the most important and frequently asked questions on the BJT and associated circuits like biasing techniques, common emitter, common base configurations, and amplifier analysis. All these question models are based on the previous year examinations of GATE, IES, ISRO, DRDO, Polytechnic Lecturers, and other state public sector unit examinations. Let's welcome to the channel Electronics Pariksha. We'll see the next question. From the measurement of rise time of the output pulse of the amplifier whose input in a small amplitude square wave, one can estimate the following parameter. See here, this is a transistor, this is the base, emitter, and collector. When you have given a square pulse here and the input, the output will be slightly delayed square pulse. It will be a square pulse, but it will be a slightly delayed one, like this. Okay, the time taken by the square pulse to raise from 10% to 90%. This is 0.1 IC, this is 0.5 IC. 10% to 90% is called a rise time. This is called rise time. We have got a formula. The rise time is equals to 0.35 divided by bandwidth. Bandwidth of the amplifier, this transistor amplifier. Or you can write this in the similar way, 0.35 divided by upper cutoff frequency. In the bandwidth, upper cutoff frequency will be there and lower cutoff frequency will be there. You can write this as upper cutoff frequency or upper 3 dB frequency. So by knowing the rise time, we can calculate the upper cutoff frequency. So answer is option B. We'll see the next question. In a transistor switch application, the operating point moves between the following regions. If you see a transistor output characteristics, it will be like this. I am observing the common emitter amplifier. These are the BI characteristics. The output BI characteristics for different IB values. This is IB1, IB2, IB3, and IB4. And respective IC values. So if you draw the load line, this is the load line. Here, this is IC saturation. IC saturation value is VCC divided by RC, whereas VC saturation is 0.2 volts. Okay, at this point, the IC will be VCC by RC, and the VC saturation is 0.2 volts. This is the cutoff point where VCE is equals to VCC and IC will be 0. So this is the state where transistor will be off. Transistor will be in off condition. So it acts like an open switch. Acts like an open switch. This is a state where transistor is on, completely on state. The transistor will be completely on state. So it acts like a closed switch. So these two are the reasons which are used by the transistor when it is acting like a switch. This application is mainly used in the digital circuits. Whereas in between area, this entire area is linear region. This linear region is utilized for amplifiers, reserved for amplifiers. Okay, this is the saturation region, and this is the cutoff region. This is saturation and cutoff regions are utilized by transistor when it is acting like a switch. Linear region, this linear region will be used by the transistor when it is acting like an amplifier. So here the answer is a cutoff and saturation, option A. The main use of the emitter follower is, emitter follower in the sense it is nothing but a CC amplifier. Input will be at the base, output will be collected across the emitter. This is the emitter, output is taken here, this is the collector. Okay, this is emitter resistance, this is collector resistance. So if you see for the common collector amplifier, this is the common collector amplifier or emitter follower, both are same. This is also called as emitter follower. So whatever the input you apply, suppose this is the input voltage VB. If you apply the Kirchhoff voltage law here, KVL, the entire input voltage will drop across the emitter resistance. So the output is approximately equal to input, that is base voltage. So that's why the input voltage and output voltage are approximately same. Output voltage by input voltage. If you see the voltage gain, it will be less than or equal to 1. So this is the voltage gain. So emitter is blindly following the input voltage. That's why it is called as emitter follower. Okay. If you see the input resistance, this is the first point. If you see the input resistance, input impedance, it is equals to beta into Re dash. Re dash is the emitter model resistance. Small resistance will be there here plus capital Re. This is a very high resistance. Similarly, if you see the output impedance is small Re dash parallel with capital Re. So it is approximately equal to small Re dash, whose value is very, very less. Practically, it will be 25 volts. So it has got a high input impedance and a low output impedance and a low output impedance. Because of these features, it is used as a buffer stage. Or impedance matching device. So the answer is option C. When the AC signal is applied to an amplifier, the operating point moves along the AC load line. Okay, the operating point, if you consider the AC signal, it moves along the AC load line. Like the video, share the video, and subscribe to the channel for better content and more videos. The next problem. In the circuit shown below, beta value is 60. The input resistance Rin is 1 kilo ohm. So what is the voltage gain? The voltage gain can be given as output voltage divided by input voltage, which is equals to output current IC by output resistance RL dash divided by input current IV and input resistance. Okay, input resistance RL. So if you see, the input resistance is given as 1 kilo ohm. RL dash is calculated like this. R dash L is nothing but collector resistance in parallel with the load resistance. So if you calculate this, 2 kilo ohms into 0.5 kilo ohms divided by 2 kilo ohms plus 0.5 kilo ohms. So this will be approximately 1 kilo ohm divided by 2.5 kilo ohm divided by 1 kilo ohm divided by 2.5 kilo ohm. So substituting the same here. Here the output current divided by input current can be replaced with the beta value and RL dash by RL. RL dash is 1 kilo ohm divided by 2.5 kilo ohm divided by Rin is 1 kilo ohm. So the beta value is nothing but 60. I'm substituting 60 here. So you will get the overall voltage gain as 20. So you will get the overall voltage gain as 24. So the answer is option B. We'll see the next question. To set the operating point at 2 volts 1 milliamp by biasing a silicon transistor with the collector feedback resistance RB. If beta value is 100, the value of RB is. So he has given the Q point. The Q point is nothing but VCE and IC, which is equals to 2 volt and 1 milliamp. So we need to find out the base resistance. If you see, he has given the collector current IC current here as 1 milliamp. Collector current is 1 milliamp. So the base current will be usually, the base current is nothing but collector current divided by beta. Collector current is 1 milliamp divided by beta value is 100. So the base current is 0.01 milliamps. Now VCE, if you see, the VC collector to emitter voltage is nothing but VBE plus VCB. So VCE is given as 2 volts in the question itself. VBE can be taken as 0.7. So the VCB will be, the collector to base voltage will be 1.3 volts. So now this voltage is now VCB. If you apply the Kirchhoff voltage law in this particular loop, you will get VCB is equals to IB RB. So the base resistance RB is equals to 1.3 divided by 0.01 milliamps. Then the RB is equals to 1.3 into 10 to the power of 5. So it is 130 kilo ohms. It is not 130, it is 130 kilo ohms. Option is answer C. We'll see the next question. Which of the following statements are correct for the basic transistor amplifier configuration? So if you see the three parameters, we have already seen the comparison of CV, common emitter and common collector. He has given the input impedance and output impedances. Input impedance and output impedance. And the current gain, voltage gain also. We'll see the comparison. The input impedance of a common base is very, very low. Whereas the common emitter, it is average, medium. Whereas for the common collector, this is highest. It has got a highest input impedance. The output impedance of common base is high. For the common emitter, it is again medium or high. Whereas the output impedance of common collector is low. It is lowest actually. Current gain, if you see, the common base amplifier has a less than or equal to 1. Whereas for a common emitter, it is beta, which is in the range of 100 to 500. For common collector, the current gain is highest, that is beta plus 1. Voltage gain, if you see, for the common base, it is high. It will be around 150. Whereas the voltage gain of common emitter is also high. It will be around 200 to 300, 450. For the common collector, the voltage gain is less than or equal to 1 because it is an emitter follower. It acts like an emitter follower. Input voltage will be approximately equal to output voltage. Now, based on these parameters, you check the options. Common base has low input impedance and a low current gain. Yes, this is true. Common base has got a low input impedance and low current gain. Common collector has a low output impedance and a low current gain. No, here it has the highest current gain. Common collector has a highest current gain, AI. So this is wrong. Common emitter has very poor voltage gain but very high input impedance. No, this is also wrong. It has got a good voltage gain and a very high input impedance. No, it has got a medium high input impedance. So fourth option, the current gain of the common base amplifier is higher. No, the current gain of common base amplifier is less than or equal to 1. It is not higher. So this is also wrong. CC amplifier has highest voltage gain. No, this is also wrong. The voltage gain of CC amplifier is, we have seen, less than or equal to 1. So correct option is the answer option A. We'll see the next question. The current stability of the CC amplifier can be increased by. The current stability can be increased. Here the stability factor is equals to 1 plus beta divided by 1 plus beta emitter resistance divided by base resistance plus emitter resistance. So stability factor can be made approximately closer to 1 by choosing the emitter resistance greater than base resistance. Okay, so this is the stability factor formula for the CC amplifier or CE amplifier. More or less it will be same. So if you see, by reducing both emitter and base resistances, no. Increasing emitter and base resistances, no. Reducing emitter and increasing base, no. Increasing emitter and decreasing base resistance, yes. Answer is option D. By increasing emitter resistance and reducing base resistance, you can make the stability factor closer to 1. Then the current remains stable. Let's see the question. The circuit shown below is. So which of the following circuits is this? So if you observe carefully, this is a PNP transistor. And this is the base, this is the emitter, and this is the collector. So to find out the circuit, first you have to find out the input and output. If you see, the base is the input, the base current is the input current, and the output is taken across the collector because the load resistance is given here. RL means the load resistance. So output is taken across the collector. So input is at the base, output is at the collector. So it must be a common emitter circuit. It is nothing but a common emitter circuit. So answer is option C. Let's see the options. The option A is constant voltage source is telling. Constant voltage source means it must be a CC amplifier, common collector amplifier. For common collector amplifier, input is at the base and output is at the emitter. Output is at the emitter, but here in this case the output is taken across the collector, not emitter. So this is not the option. Constant current source in the sense it must be a CB amplifier, common base amplifier, whose input is at the emitter. Input is given at the emitter and output is at the collector. Output is at the collector. So even that is not correct. So here in this case, this must be a constant, a common emitter. We'll see the next question. The CC amplifier has, the common collector amplifier has, which of the following? It has got a very high input impedance and a very low output impedance. We'll see how it is. This is a common collector amplifier. Input is given at the base and the output is taken at the emitter. Emitter will have the RE, emitter resistance, but there is small internal resistance also. There is a small internal resistance, that is RE dash, emitter model resistance. And there is a capital RE whose value is very high. Output is taken across here. This is base and this is collector. This is a common collector amplifier, basic model of the common collector amplifier. If you see the input impedance is nothing but, if you see from this particular point, it is VB divided by IB. Okay. If you apply the Kirchhoff voltage law in this loop, assuming this point as a VB, built-in potential, we'll get VB is equals to IE emitter current RE dash plus IE emitter current capital RE. So the emitter current can be written as beta plus 1 IB and RE dash plus capital RE. So now the input impedance, that is VB by IB, base voltage divided by base current, is beta plus 1 times of small RE dash plus capital RE. So usually the beta value will be very high. It will be in the range of 100 to 500 and RE value also will be very high. It will be in some kilo ohms. So the overall input impedance is very high for common collector amplifier. Similarly, output impedance, if you see, output impedance must be taken from the load. This is the emitter resistance. So you have to look from this point of view. So here the emitter resistance RE and the emitter model resistance RE dash will come in parallel with each other. So the output impedance is nothing but capital RE in parallel with the small RE dash. So when two resistances are in parallel, the equivalent resistance will be the lower than the lowest resistance. So here the output impedance will be approximately equal to RE dash, because RE dash is very, very low. This value will be very, very low. Usually the RE dash is nothing but RE dash is equals to VT divided by IE. The thermal equivalent voltage is nothing but 25 millivolts, and the emitter model current will be emitter current will be in the level of 1 or 2 milliamps or 10 milliamps. If you substitute that particular value, you will get it will be around ohms, some 2.5 to 25 ohms. So very less. So when capital RE and small RE dash, that is emitter resistance and emitter model resistance, come in parallel with each other, the output resistance will be equivalent to emitter model resistance, the smallest resistance. So the output impedance is very less. Output impedance will be very low. So the answer is high input impedance and low output impedance. That is option D. We'll see the next question. For a common emitter BJT configuration with the common collector terminal resistance R, the slope of the DC load line can be. So if you see the circuit, this is the circuit. Like the video, share the video, and subscribe to the channel for better content and more videos. This is the resistance, biasing resistance R1, and this is the resistance R2. There is a transistor, and he's telling there is a collector resistance RC. Usually collector resistance is denoted with RC, but here he has denoted with capital R. This is the circuit. Output is taken across this capital R. Now he's asking the slope of the DC load line. First we'll write the equations for the DC load line. If you apply the Kirchhoff voltage law in the output loop by applying KVL at the output loop, we will get VCC is equals to ICRC, that is collector current and collector resistance. The collector resistance is denoted with R plus VCE. Now, from this, the collector current equation IC will be equal to VCC minus VCE divided by R, which can also be written as collector current IC is equals to minus VCE divided by R, or I can write like this, minus VCE multiplied minus VCE multiplied by 1 by R plus VCC. Now, if you observe, this is in the form of Y is equals to mx plus C. mx plus C. Here also there will be R. So, here the y-axis is nothing but collector current. If you see, the output characteristics will be like this for the load line. This is the collector current IC and this is the common emitter voltage VCE. The output characteristics will be like this for the common emitter amplifier. The load line is drawn across the output characteristics. This is the IC saturation, the maximum point. This is VC saturation, the minimum point. IC saturation, VCC. Okay. So the y-axis is nothing but the collector current. X-axis is VCE, common collector to emitter voltage. So the slope M is equals to minus 1 by R. So the answer is option D. We'll see the next question. The DC current gain in the common collector configuration is given by. See, this is the common collector amplifier. There is a transistor. Input is given at the base. The output is taken across the emitter. This is the collector. Input is given at the base. Output is taken across the emitter. So the current gain gamma is equals to the output current emitter current divided by input current base current. So gamma can also be written as the emitter current is nothing but the sum of base and collector currents. So which can also be written as 1 plus IC divided by IB. IC by IB. This is for CC, common collector configuration. If you consider the CE configuration, input is at the base, the output is at the collector. This is the common emitter configuration. So for this, the current gain beta is equals to output current collector current divided by input current base current. So by substituting this, gamma is equals to 1 plus beta. This is the answer. So the answer is option A. The DC current gain of common collector configuration, that is gamma is equals to 1 plus beta. The same gamma you can write in terms of alpha, that is 1 by 1 minus alpha. Alpha is nothing but the DC current gain of common base configuration. The DC current gain of common base CB amplifier. Okay, these are all important formulas. Gamma is equals to 1 plus beta. Gamma is equal to 1 by 1 minus alpha. Similarly, we have beta is equals to gamma minus 1 and beta is equals to alpha divided by 1 minus alpha. Okay, these two conversions are also very important. Now let's see one more question. The following transistor configuration circuit is much less temperature dependent. That is common base, common emitter, common collector, none of this. Answer is common collector. Why? Because if the temperature increases, the reverse current in the transistor increases, IC naught. So if IC naught increases, in turn that increases the collector current. So if the collector current increases, again the power dissipation increases. This will further increase the temperature and this cycle repeats. So if the temperature basically increases, it will affect the collector current directly. Here we must understand two things. That is here. If this is a transistor, this is emitter, base and collector. Emitter constitutes 100% of the current. This is called direct current. So when the electrons are moving from emitter to base, base will constitute 5% of the electrons, 5% of the current, and the remaining 95% will be pushed into collector. This entire thing is the direct current. So here the collector current, IC, collector current has two components. One is a direct current, which is primarily influenced by emitter current. So if emitter current increases here, if emitter current increases, the collector current, direct current also increases. Okay. So this direct current component is influenced by emitter current. The collector current has one more component, that is IC naught, which is nothing but a reverse current. This IC naught is the reverse current. This is influenced with temperature. So if temperature increases, the reverse current increases. Okay. So if the temperature increases, reverse current increases, IC also increases. But you cannot make it equivalent to the increase in emitter current. Okay. If the temperature increases, IC not increases, and hereby the collector current increases. That doesn't mean that emitter current also increased. No, that is not correct. We can give this formula: emitter current is equals to base current plus collector current. Here we are telling the collector current increases because of temperature, reverse saturation current. So this will increase the emitter current also. But that concept is not correct. It is wrong. Why? Because due to temperature, the reverse saturation component is increasing and collector current is increasing. But the direct component remains constant. The direct component majorly depends on emitter current, which remains constant always. Okay. That's why the common collector configuration, the input is the base current, output is the emitter current. Both currents are independent of temperature. Both currents remain same, independent of temperature variations. If collector current is involved, we have to say they are temperature dependent. But here nowhere the input and output are independent of collector current. So this particular circuit is less sensitive to temperature. Whereas in case of common base and common collector, output current is collector current. So collector current keeps varying with respect to temperature. That's why these two circuits are temperature dependent. Whereas common collector is not temperature dependent because output current is emitter current, which majorly depends on the applied input voltage, not on the temperature. Okay. Hope you understood this. We'll see the next question. The common emitter amplifier circuits are preferred over common base circuits because they have large amplification factors. We'll see the gains of a common base, common emitter, and common collector. Just a little comparison so that you will try to understand the gains between these two things, these three configurations. Okay. Now, if you see the gains, the voltage gain of a common base will be approximately 150. Whereas for the common emitter, it is approximately 500, in the range of 500. For common collector, this is less than 1. Similarly, current gain, if you see, current gain for the common emitter is less than or equal to 1 because the input current is emitter current, output current is collector current. Both are approximately same. Whereas for common emitter, that is equals to beta, whose value varies from 100 to 500. For the common collector, it is beta plus 1, the current gain. Next, power gain, if you see, power gain is nothing but the multiplication of voltage gain and current gain. So you can calculate this will be approximately 150. Whereas here, this will be highest. The power gain will be highest because the voltage gain as well as current gain both are high values. Here, this will be approximately equal to beta plus 1 only. So if you compare these three configurations, CE, common emitter configuration has good number of gains, large amplification factor with respect to voltage, current and power. So CE is more preferred compared to CB and CC also. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.